Kalyan sir, are you online, sir?
Can you hear me?
Sir, are you online? Yes, sir, you are audible, sir. Sir, should we proceed with your talk right now?
Yeah, sure. Can you hear me?
Okay, sir. Okay. Yes, sir, you are
I'll
audible,
share my
sir.
slides.
Should we proceed with your talk
please.
right now?
Yeah, sure.
Meanwhile, you can introduce.
Sir, can
I'll share my
Yeah,
slides.
just yeah,
Sure, sir, please.
just a second.
yeah. Please sit down. You can introduce.
Sir, can
Yeah, just yeah, yeah. Please sit down. You can introduce.
Kalyan.
Can yeah, just yeah, yeah. Please sit down. You can introduce.
Kalyan.
Can yeah, just yeah, yeah. Please sit down. Can
Kalyan sir, let us wait for 5 minutes because it seems that Professor Kim can reconnect.
Okay, sure.
Kalyan sir, let us wait for 5 minutes because it seems that Professor Kim can reconnect.
I just reconnected.
Okay,
So,
sure.
Kalyan sir, let us wait for 5
wh-
minutes because it
which
seems
slide
that
did you
Professor
see?
Kim can
I
reconnect.
just reconnected. So, how about this one? Which slide did you see? This
Sir,
one?
the slides are not
Sir,
shared.
slides are not shared right now.
How about this one? Which slide did you this
Sir,
one?
the slides are not
Sir,
shared.
slides are not shared right now.
How about this one? Which slide did you this
Sir,
one?
the slides are not shared.
Slides are not shared right now.
How about this one? Which slide did you this
Sir,
one?
the slides are not shared.
Slides are not shared right now.
এটা বন্ধ হয়ে গেল। এটা বন্ধ হয়ে গেল।
Could you give me the authority for the sharing could you give me the
Oh, sorry, please.
Sir,
for the sharing?
Yeah.
sir, can you just please email it to us?
Sorry, please.
Sir,
as such, there is no
Yeah.
as such, there is no restriction to
restriction in sharing. Sir, you can just please share your screen only. It will be visible to us. Sir, you can just please share your
Can
screen
you see it
only.
now?
It will be visible.
No, sir.
Not yet, sir. Not yet.
Can you see it now?
It will be visible.
No, sir.
Not yet, sir. Not yet.
Can you see it now?
No, sir.
Not yet, sir. Not yet.
Can you see it now?
Yes, sir. It's visible, sir.
It's visible,
Yes,
sir.
it's visible, sir.
Yeah, which slide did you see? Did you see this or this?
Yes, sir. It's visible. Sir.
Can you just go a little behind?
Slide did you see?
So, can you just please go a little bit behind? I mean, some slides behind.
I guess
Behind.
a little behind.
Yeah.
How about
Can you
this?
just please go a little bit behind? I mean, some
yes, he is
slides
discussing
behind.
this.
Behind. Can you, did you see this?
Sir, actually, we saw the artificial muscles up to that slide.
You mean this?
Actually, we
Yes.
yeah,
You mean this?
muscles. Yes, sir. Yes, sir.
Probably
Yes,
the.
I've
You mean this?
like this, sir. This one. Yes,
Did you
this
see the
one.
movie?
At that time only.
At that time only it got disconnected, sir. This slide only.
Probably movie is too heavy. Then
Maybe
yeah,
at that time only.
probably I don't want.
Disconnected, sir.
Can I try one more? Probably movie is too heavy.
It's not required, sir. You can just.
You just can you please just conclude.
Try one more. Probably movie is too heavy. Okay,
If
so
it's not
okay.
required, sir,
Then
you can just.
anyway, right?
You please just conclude.
I could attain very high performance, right? So okay. Artificial muscle based on graphene based composite structure. And let me move to Dr. Mighty's work. This is about using graphene oxide liquid crystal for the 3D graphene assembled structure. And actually, in the this version of graphene oxide liquid crystal, Dr. Mighty simply immersed zinc plate, and then he obtained a large area, right? 3D graphene porous structure in a very high yield. Actually, the underlying principle is electrolysis deposition. When zinc is dissolved in graphene oxide aqueous dispersion, the graphene oxide is reduced due to the reduction potential difference with zinc. And actually, he could also obtain layered composite structure by incorporating nanoparticles and nanowires. And he could also obtain this structure at the surface of textile, right? Flexible textile. And even at the 2D pattern or 3D pattern template structure, so it's a very versatile, right? 3D carbon assembly. And recently, my group member attained the same approach of electrochemical assembly for of machine, learning from Dr. Mighty, and we could also obtain 3D macroporo structure of machine based on this approach. And next one is Marangoni effect. Actually, I told you that surface tension can be useful to make right this kind of this is real-time movie showing the 2D material assembly at the water surface. Originally, graphene powders particles are dilutely dispersed over entire dispersion, but they spontaneously floated at the surface and undergo lateral assembly. And the assembly is very dynamic, like a living system. So we could attain 10 centimeter diameter assembly in a 2-minute process. And we also obtained this, apply this approach for the machine assembly. Machine is hard to obtain large area film, mixed film, because if you use typical vapor deposition, it tend to form max bulk phase rather than machine thin layer. So only one way is to use exfoliated graphene platelets to have assembled in the 2D structure. So that's why we used Marangoni effect. And by incorporating this our method, we could obtain well-defined, right, large area, minimal stacked machine film, and identify the EMI shielding impact of this material. And I also worked on the chemical modification of graphene-based structure. Actually, and pure carbon graphene can be interesting for electrical property, for mechanical property, but in the energy and environmental application, you would like to have a controllability of chemistry and surface energy and reactivity, right? To this end, actually, you really need, right, chemical modification such as heteroatom doping. Actually, we encountered nitrogen doping of carbon nanotubes during our old PCBD growth. Actually, we found that there is a spontaneous formation of single atom catalyst. Actually, iron metal was obtained from bottom metal catalyst, and nitrogen was supplied from ammonia environmental gas. And actually, we could also identify there is a single atom catalytic effect from this metal center. And our discovery of this behavior is nowadays evolved into single atom catalyst research area. And you can also find our recent review article summarizing this prospect for the single atom catalyst. And nitrogen doped carbon can be also useful for the unzipping of carbon and bifunctional catalyst synthesis and high performance hydrogen evolution catalyst and lithium battery anode formation, right? And if you are interested in our graphene oxide crystal, as I introduced in the most of my part of my presentation, you can find this review article published in Chemical Society Review and APL materials. And as I mentioned, our graphene oxide crystal can be commercialized. Actually, I made a startup company, and we are collaborating with a graphene production company to have a high mass production, ton level production of high quality graphene oxide and few layer stacked high quality graphene. And we also try to make some commercial products such as graphene incorporated new functional fibers in the market. Okay, so that's the end of my talk. I would like to thank all the organizers and attendees. Thanks very much. That's the end of my talk. I would like to thank all the organizers and attendees. Thanks very much.
Couple of questions, sir. Sir, we have some questions. So the first question is from Nishita. So she's asking, when we deposit 2D materials few layers on substrates, why it is triangular or hexagonal star-like shape?
Hexagonal, triangular?
Why it is? I mean, sir, she's asking when we deposit these 2D materials in a few layers on any substrate. So why does it take this triangular or hexagonal kind of shapes? In a few layers on any substrate.
Actually, the shape of the 2D material is arbitrary. It's not well defined. So there is no regular packing. But in our this kind of right, this kind of Marangoni effect, there is a strong Marangoni effect to have a close packing, even though each particles are irregular. So there is a minimal probability to have a void. That's the advantage of this process. Very interesting behavior. You see, graphene plainless are right. Weakly let overlapped at the edge, but usually, mostly they are rather almost monolayer or double layer. Very interesting. Is it fine? Mostly they are rather almost monolayer.
Yes, sir, absolutely. Sir, if there are any more questions, we will write directly to you so you can answer it.
Oh, sure, yes.
Absolutely. Okay, sir. Thank you so much, sir, once again for your enlightenment.
Oh, sure,
We are now
okay.
moving towards our next talk. Okay, sir. Thank you so
Thank
much,
you.
sir, once again for your enlightenment. We are now
Okay.
moving towards our next talk.
Okay, so Professor Kim, this is Dr. Maiti. Thank you
Uh-huh.
for your thank you for your illuminating talk. So just one point I would like to ask. So when you are using this polydopamine, so when I would like to ask conductivity or you are using this polydopamine. So when
I cannot hear you, but probably it's about electrical conductivity from the dopamine ingredient, right?
yes.
Actually, after this dopamine incorporation, we do very brief thermal reduction
Okay.
at about 1000 degrees Celsius. And in this condition, dopamine evolved into nitrogen doped carbon.
Oh,
So
okay, got it.
conductivity can be also enhanced as a result of this doping effect.
Okay,
Good
thank you.
question. Thank you.
Okay,
Good question.
Thank you so much, sir,
Thank you,
for your
sir.
enlightenment.
Thank you very much.
Thank you, sir.
Thank you, sir.
Now I would like to invite Professor Kalyan Raidungia for the next session. Professor Kalyan Raidungia is a professor at IIT Guwahati in the Department of Chemistry. He has submitted his doctoral in the year 2011 from Jawaharlal Nehru Center for Advanced Scientific Research, Bangalore, India, followed by postdoctoral until 2015 from Material Science and Engineering Department, Northwest University, Illinois, US. He was also awarded DST Ramanujan Fellowship from Science and Engineering Research Board in the year 2015. His research focuses, but not limited to, material science, nanofluid, and nanomaterials. His title of his talk is Energy from the Nanofluidic Transport of Water Molecule, where he will be discussing about harvesting of electrokinetic steaming potential from steaming water through bioconical nanofluid channels using closed-packed monosphere. Participants are requested to mute their mic. They may put their questions in the chat box, which will be answered after the session. Over to you, sir. They may put their questions in the chat box, which will be answered after the session. Over to you, sir. Sir, are we audible to you?
Kalyan,
Kalyan, sir, your mic is unmuted.
Okay, can you hear me now?
Yes, sir,
Yes, sir,
yes,
you're
sir.
audible, sir.
You're audible.
Okay. Thank you very much for the nice introduction. Can you hear me now?
Yes, sir,
Let
yes,
me
sir.
share my slides. Thank you very much for the nice introduction. Can you hear me now? You can see my slides, right?
Yes, sir, we
Yes,
can.
sir, visible, sir.
Okay. So I'll start now. You can see my
Yes.
slides, right? You
Yes,
can
sir, we
see
can.
lots of talks regarding the energy part. So we will also
Yes.
discuss a slight different approach in the energy field. So before going to start my actual talk, I'll just give a brief overview of the kind of area our group is working. So we work in a very broad area of material science where we're trying to create new properties by tuning structure of different materials at different levels. So once we tune the structures, we get different properties, and based on the properties, we try to find some suitable applications for materials. And once we have a target of particular applications, and we don't have a material of desired properties, we can go and tune the structures to get the same. So this is actually a very broad area probably this can be connected to most of the research areas going on currently. So these are our key application areas, like preparing smart materials, sustainable energy harvesting, nanofluidics, water purifications, and so on. So just to give you an example, like what kind of properties can be obtained just by tuning its structure. We all know clay minerals. This is very common everywhere. Like we are connected to clays. There are two components like montmorillonite and vermicullates are two common clay minerals. These are always mixed together, but we can separate them and make individual film out of them. Again, put them one by one, one top of each other, just to change the structure. Then we can see we can get different kind of smart material or responsive material based on the just to structure tuning. Similarly, we can also tune further a little bit of structure. We can get self-healing materials which heal their damages just like our own skin or like biological materials. So this is the power of structure property relationship that we can achieve through this one. So but today our main talk is on the energy. So as we already have listened to so many energy talks, there is no doubt that currently energy is a big topic. Everyone is looking for energy to solve this problem. So like many of the scientists around the globe has a new view on this energy problem, so which is called decentralization of energy sources. So typically what happens, energy is created in a big plant like electricity generation or a thermal plant where it's generated and distributed to different area where it is used. But according to this new concept, it will be much better or much easier to solve this crisis if we decentralize the energy sources. Instead of preparing a large source in large amounts, if you can make so many devices which can be used in the household environments to create energy and different way, like every house can prepare their create some device, buy some devices or install some devices which will give sufficient energy to for their use, as well as the excess energy can be sold out to give to the places where more energy is required. So in that case, it will have a huge impact on the economy and the energy problem will be solved in a much better way. So to have this, we need to have like a different sources or areas where we can create large amount of energy in the domestic environment. In that, every household can do that. So whenever we talk about the energy in the sustainable form, the water always come into the picture. For example, we can see these pictures from Mesopotamia in 4000 BC, which suggests that at that time itself, water which is used to prepare the mechanical energy of the water is transformed into different forms like grinding, milling, or lifting. All these things can be done from the mechanical energy of flowing water. Similarly, around 1905, 6, like people started using a big dam, preparing a big dam to generate electricity, which is now one of the like major contributor of sustainable energy. So there are some problem with this dam, like even though it is very useful now, like we need to have a certain requirement of natural places. We cannot put this dam everywhere. Moreover, whenever we put a dam, it creates sufficient threat, a magnificent threat to the locality, as well as the ecosystem is like destroyed for a large area. So again, this kind of thing, it is very difficult to put in the household environment, so we should not put us in the decentralized systems. So very recently, so people started to find as alternative energy sources. One of the process is like when we flow water through small nanofluidic channels, then we get some energy. So this is a like a very small channels in the nanometer range. Then we can multiply these channels in large amount to get some energy, useful energy in the domestic setup. So we also work, some part of our work is based on this process. So we can see different devices where we can get some energy from household, our water taps, or like from mechanical energy can be transformed into this kind of things. And there are not only us, like many other parts of the world, like people are working this kind of energy harvesting from small flow of water to nanofluidic channels. So I'll talk mostly about the theory and some introduction behind this kind of energy generating processes. So before going to the actual process, I'll just say like how it started. It started like this electrokinetic phenomena is very early, before 1800 itself, like where some curious people, curious mind started worrying uh, about the observation they made everyday life. Like us also, we see that some clay solution, if you take a clay in water, it form a very stable dispersion. Similarly, our blood is also a very stable dispersion of colloids. Like solids are dispersed in water without even dissolving. It's not like sodium chloride or potassium chloride, something which completely dissolve. The solid is still intact, but they can form a stable dispersion in water. So now we understood very well that all this solid has some electrical charges on its surface, and based on this electrical charge interaction with the medium, dispersing medium, it forms a stable dispersion. But it was that time not very clear. So what studies goes back to 1798, where the first uh, Alessandro Volta prepared the first battery, you can say, first battery where he connected multiple layers of zinc, silver, or copper plates, which is sandwiched between sodium chloride in water to prepare some kind of early stage battery. Then where he can tune the number of layers as well as the diameter of these layers to control the voltage and current he want to get. So this was very exciting at that time. This was the first system where you can generate electricity or apply electricity at your own with a control manner. It was very difficult otherwise. So once he showed a way to produce electricity in a controlled manner or applied in a certain places, different people started applying it in various areas and made some significant discoveries. So around that time, around 1808, so one scientist, German scientist, I think, did a very interesting experiment based on his observation with clay minerals. So what he did, he took a U-size U-shaped tube. Then he put a quartz membrane, this gray part here, and then on top of that, he put some clay minerals there, clay, normal clay. When he applied the voltage between these two ends, then he can see that some of the clays are coming through the filter, through the pores of the filter, and going to the other sides. It gives an indication that all these solid particle, what was like initially they were confused, actually have an electrical charge. Otherwise, they would have not moved with respect to or with response to an electrical field. Similarly, he did another experiment where he made a filtration setup, kind of a plug of cotton, clay minerals or soils. Then he applied the voltage. Then he can see that water level is rising in one side and decreasing in one side just by applying voltage. So this is now the known as the electroosmosis process. Actually, what happens when we apply a voltage, then clays have negative charges, then only certain ions, like if it is negative charge, only cations are allowed to go to the pores mostly. Then once the ions are selectively gone from one side to other side, to compensate the ions, the concentration of excess ions, water also followed through the osmosis process. So the water level increases. So this is a very interesting experiment, and this is known to be the starting point of the electrokinetic phenomenon. So what we know by this, that if you apply voltage through a charge selective or charge filter, then ions can move through one side, and which will generate the pressure difference, which is electroosmosis. That water level is changing means the pressure in both sides is changing. Similarly, a reverse experiment was done by George Quique in 1859. What he did, he assembled large number of capillary channels. At that time, like around few 10 micron or so radius capillary could be made the best, because we are talking in very early times when you put large number of uh, capillary channels in a U-size device, U-shaped device. Then he applied a pressure. from that liquid is moving from this side to this side, from left to right. And now this time when he applied liquid, pushed the liquid to the capillary channel, he can see generation of a voltage around the two sides. This is just opposite to the electroosmosis process where voltage was applied to push the liquid from one side to another side. Now liquid is pushed from one side to another side, then voltage is generated. So this is the starting point of, probably you can say, energy possibility of energy harvesting through electrokinetic effect. But the problem was like the efficiency was very low. The amount of energy one have to apply to push through these small channels, and that is not sufficient to get enough energy to compensate for that energy. So even though it was known to us like very early, around 1859, it is no energy harvesting device is there based on this principle yet. So, but still it was studied very with lots of theoretical and experimental systematically. And Helmut Smolsky developed a very wonderful theory which can be quantify this the potential generated by this process. For example, the potential streaming potential is inversely proportional to viscosity of the water and specific conductivity of the water, but it is directly proportional to zeta potential and pressure difference in both sides. Similarly, current also they have a very quantitative analysis. So even though it was not attempted for energy harvesting process, it is used for like early detection of earthquake or volcanic eruptions or such thing, because all the groundwater has ground has some water. So during these major events, this water moves through the clay or the soils. When the water moves, then it generates a voltage or a potential difference, so which can be an indication of these big natural events. Similarly, when liquid or fluid, like for example, crude oils are flowing through big pipes for a very long distance, it also generated so much potential, which is like considered to be a major cause behind many major accidents or like a breakdown, fire breakdown, and all these things. So based on those contexts, it was studied vigorously. But with the around 2000 or so, when now new technologies came, we can prepare nanofluidic channels of very small dimension, is large amount. Then this concept of harvesting energy in a small scale by using electrokinetic potential became again relevant, and people started working on this again. So I will again give you a brief overview actually what happened in this process. So far we know that whenever we have a solid surface, most of the solid surface, when you put it in water, it gets some kind of charge. Some may be very high charge, some may be very low, unless it is a like perfect graphene sheet without any defect or a carbon nanotube. So most of the solid will acquire some charges when you put it in water. So in this, suppose our solid is of negative charges, it will attract some of the positive charges around it. And we can see near the surface we have more positive ions. As we go away, it's become almost neutral, like positive and negative become almost equal size. So the distance up to which there is a significant charge separation is called the Debye length. And that entire process is called also electrical double layer. Now the interesting thing about Debye length is that it is only dependent upon concentration of the solutions. So this is the equation which the Debye length can be divided. So for example, it's standard conditions, everything is under standard conditions, then it's 0.304 divided by root of the concentration. For example, for 10 millimolar concentration solution, the Debye length is around 3 nanometers. Now, whenever we make a bulk channel or any pipe, we always have this Debye length. But the size of the pipe is so big, this small Debye length is become very insignificant. So we don't see a very significant effect because of this Debye length. But nowadays, we can make a large number of channel of very small size. For example, these two surfaces are coming very close to each other. Then this Debye length overlap. Now, once this Debye length overlap, all the no matter what is there in the solutions at the outside, in that overlapping regions, we'll have ions only of opposite charge to that of the surface. If surface is negative charge, if channel is very small, all the channels will be occupied by cations. And this concentration of cation will depends upon the number of charges on the surface. So this is a region which is called surface charge governed regions. We can easily find out whether a channel is where electrical double layers are overlapped or not, because we know the ionic conductivity, right? Ionic conductivity is nothing but like it is directly proportional to number of ions in the solutions. And if we, this is the curve, red curve, you can see as we change the concentration, increase the concentration, the conductivity increases. This is a normal thing, bulk channels. But when this dividers overlap, so even though we are decreasing the concentration of the solutions, this is the blue curve, the conductivity not decreasing. That is because even though outside concentration is less, because of the surface charges, the channels will be occupied with a fixed number of ions. The surface will attract these ions from the channels and will neutralize their surface charges. So even though you are decreasing this concentration of orders of magnitude like 1,000 times, 10,000 times, the conductivity will remain same. That means the concentration that you will be same. This is called surface charge governed ionic conductivity, which is a very characteristic of a nanofluidic channels. So we'll just slightly move now. Now, like lots of people are preparing, adopting different methods to make channels with overlapping electrical double layer and using for different applications. So we also have a developed different techniques which is based on the 2D layers like graphene oxide and boron nitride, BCN, vermiculite, MOS2, WS2, like so many 2D materials you people know now, like all the talks and everyone knows now 2D materials. So these 2D materials are very large sheets, which like a length to thickness ratio. The thickness is just 1, 2, or maximum 10 nanometer, and the width is like tens of micrometer, a very large aspect ratio. So when we allow to settle down, in the previous talk also, team talk also, you can see that when you allow to settle down these large to these sheets, they always fall one upon another, and they try to form a stacking. And once they form a lamellar structures, between the layers, there is a very small space in the range of 1 nanometer or less than 1 nanometer, sometimes slightly higher than 1 nanometer. And in this, we have, if we allow to settle down so many 2D sheets, a large number of 2D sheets, we can get thousands of nanocell in a very small area between this space. And we have shown in earlier that this space can be used as an nanofluidic channels, and where we can study transport of mass and molecules or ions under extreme confinement. And this again, showing this surface charge governed conductivity is a proof that we actually form this kind of nanofluidic channels by this method. So this kind of nanofluidic channels are being used in different areas like water purification, ion pumping, chemical reactions, and so on. So we also try to prepare such nanofluidic channels, a large density of nanofluidic channels for and so on. And this energy harvesting from streaming potential process. And for that we have prepared a clay-based nanofluidic device, which is by taking a vermiculite clay and did the necessary characterization. I will not go for this. But then when we made a device and try to push water through it, we definitely got some voltage which is very small, just like 12 or 13 or like 15 millivolt range. But this is like it's good for the proof of concept, but not for the realistic application. The reason the voltage was very small is that this is the channels are so small. When it is 1 to 2 nanometer range, it is very difficult to push liquid through it. It is extremely difficult. So therefore, we tried to open up the channels. We put some spacer or make a large plex. Here again, like liquid can go through very fast for these channels, but again, power is very small, like 50 to 100 nanometer range. So the problem is like there is a competition. If channels are very small, liquid flow is very small. so we don't get any energy. If channels are large, liquid will flow very fast, but nanofluidic confinement will not be there. The overlapping of the Debye layer will not take place, and because of this, will not get any energy, because without overlapping Debye length, nothing will happen. So therefore, we can go for an alternative system where we can assemble large number of monodisperse spheres one upon another. So this, from our higher secondary knowledge itself, we can know that when monodisperse spheres are allowed to spill on one upon another, there are some vacancies between the spheres, some tetrahedral and octahedral vacancies, and these vacancies are not random. They are very well defined and connected to each other through one well-defined channels. And we can see, if you can a little bit imagine this connection between the holes, these vacancies are can be some biconical pores, like our glass shaped pores we have. Now, once this kind of pores we have, it is both theoretical and experimental shows that more than this cylindrical or square shaped pores, liquids can migrate much faster rate from this biconical pore shapes. And there we can again tune the size to tune the overlapping ED layers uh, to, to have some desired properties. So basically we prepared spheres, silica spheres, by a simple process called Stover's process, where just tuning slightly its parameters, we can make spheres of different sizes. Then once we made these different sizes, we pack them in a syringe, and in the syringe itself, like between the spheres, we put two electrodes, copper wires, and we started pushing liquid through this. And as soon as we push liquid through this, we can see a good amount of voltage, say around 120 volts to 150, 1.5 volt to 1 volt range, which is almost like 100 times more than the what we got with the highly tight nanofluidic channels. This is a large improvement. So typically, like so far, whatever paper were published before that, most of them were dealing with microwatt per meter square range energy. Just by tuning these channels, we can increase like almost 100 times more power. Similarly, we can also have spheres of different dimensions and see like what dimension shows the maximum power. Then we can see that I'll not go to very details in this channel, but we can directly find out from the calculation what is the dimension of your spheres that is directly related to the dimension of the holes or the vacancy between the spheres. For tetrahedral holes, it is 0.225, and for octahedral 0.414. Then we can find out from that we use mostly DI water, which can be considered as 10 to the minus 6 molar concentration. So Debye length we can calculate to be around 300 nanometer. Then we can see this around 1750 nanometer size pores. We have most of the bigger pores, but as well as overlapping Debye layers, because Debye layer will be from both sides of the channels. But as we go beyond that, the pores will become what will flow fast, but Debye layer will not overlap. That is why you can see this curve around these spheres. 1750 nanometer size spheres, we can have a maximum overlapping of Debye layer. As the high flow rate, we get a maximum. And so we can again like use this is a simple setup. Just to, we can use our tap water to pump some of the liquids through the aspirator pump with get a vacuum. Then we can get some decent amount of energy. It may not be sufficient to do a big sort of work, but a small amount of supplement energy is sufficient to charge your mobile or some small devices in the household environment, which can be again like scaled up to make a big device, or like multiple devices can be added up to get some things important. Now, even though like this was a very drastic improvement, as we say, we still have to apply some kind of pressure to push the liquid to the channels, which is again not very convenient. So we can find out alternative ways to push the liquid to the channels, which will give us sufficient energy to run some of the IoT kind of devices. For example, some places we need to set up some devices where going there able to charge the mobiles, charge the batteries, or like giving power is very difficult. For example, some night vision cameras installed in the forest to monitor the animals and all. So many things like that is there where we don't want to physically present there, as well as we don't want to charge the equipment there on daily basis. So for that also we can have a device based on this principle, by using evaporation as a driving force to push the liquid through the channels. As you can see from these slides I have taken from the internet, that any moment the atmosphere contains around 37.5 million billion gallons of water, it seems, which is invisible. And this amount of water is recycled 40 times each year. That means a huge amount of energy is being used without our knowledge to evaporate the water and coming out rain. This is a huge energy. So if you can use this evaporation energy to draw the liquids through small nanofluidic channels, we may be able to get some useful electricity without investing any fuel or work or something. Okay, for that we again took help of the 2D nanomaterials, where for a proof of concept we prepared vanadium pentoxides to these sheets by using hydrogen peroxide in ice cool conditions. Then we can prepare a freestanding membrane. These are the channels, and this surface charge governed ionic conductivity curve shows that we actually have a well-defined nanofluidic channels in this layered materials with so many channels in it. So here what we can do, we can put two wires at both end of the device, then keep bottom part of it to a liquid water. And we can see as major part of the device is exposed for evaporation of water, we can see a very good amount of stable electricity coming. So we don't have to do anything, just make a device, put in some kind of water source, then water will be evaporating by itself through the channels and we get some energy. And to confirm that this evaporation is the driving force for this energy, so we can seal this device, like we can just close the lid, we can put in a beaker and close the lid so the evaporation is stopped, so voltage generation will be stopped. Moment we take out the lids, evaporation starts again, this energy generation begins. So like this, like not only us, many other people also have done this kind of experiment. But the problem here is like when you dip the actual device in a realistic situation, in a lake or river or somewhere, so there is a chance that accidentally this device may be damaged, or like a level of water can change with time during dry season, hot season. So someone has to go and again visit it at the proper region. We can see that if we dip the device too much, then again energy generation stops. So therefore what we can do, we can take a filter paper or a cloth or something which is dipped into the water, then the end of the paper is touched to the our active device. Now whatever water is coming through this paper or a wet cloth, we have tried so many things here, then that is sufficient to run the device and get some energy. For example, here my students proposed a concept of boat where so many clothes can be hanged to the river, and this clothes will bring some water through capillary force and it will give device. Then we have 6 devices, and we get sufficient energy to operate a calculator which is hanged on the lake or something. Similarly, in the large scale, probably it will give us some extra energy which will be very useful for our daily applications. Similarly, another concept came up where we can create an artificial hydrological cycle, where one end of the device will collect the water from the atmosphere, then the other end will evaporate the liquids, and this is a natural process. We don't have to apply anything. Then during the process, we will be able to get some of the energy from the environment. So based on this concept, we have prepared a material, hygroscopic materials, which is agar, glycerol, and lithium chloride. This material is so hygroscopic. Moment you put it in atmosphere, it will collect so much water from the atmosphere. It almost feels like it's weight always. So here we can show that this is the weight of the film. When you put it extreme dry conditions, even after 4 hours, there will be no weight loss at even 10% humidity level. After that, it will slowly decrease and it takes up to 22 hours to completely dry. Now, when you put back again to atmosphere, within 4 or 5 minutes, it regain all its energy. Up to 80, at 80% humidity, it's regained all the water molecule it left. It dehydrated in 22 hours. Now, when we connect our device to these hygroscopic materials, which will collect water from the atmosphere, at other end of the device, this water will be constantly evaporating from the through the nanochannels. Then we can, without anything, we can just put this device atmosphere, and we can get energy for a very long times. So which will be a self-sufficient energy giving device. But anyway, we need to have lots of improvement and improvisation to take it to realistic system. But this is a very nice proof of concept. You can see up to 36 hours without any intervention or without any fuel, we can get some energy. So this is the another last example I want to show you, because I don't want to take up so much time. It's about to have lunch time. So we can also use this concept to harvest some of the waste heat. So we know like heat is a universal form of energy, right? It used from cooking to like making big machinery or like flying rockets and everywhere. It's a waste heat is one of the heat is everywhere. Every day, every household use heat. And the problem with heat is like only 30 or like a maximum 40, in the best possibility 40% of heat is used for actual work. For example, when you cook something, only 30% of energy is used for heating the liquid inside or cooking the rice. Rest is going out as a waste to heating the environment or the surroundings or the utensils. Similarly, even cars, also best possible car also, major part of the heat is getting wasted as a heat, not for moving the car. So if you can have some mechanism to harvest some of this heat, even like 10% of heat, waste heat, if you can harvest any form, it will be a big amount because the heat is everywhere. The amount of heat getting wasted is too massive. Even like 5-10% if you can harvest, it will be a deal. And people know about it, and from very early, around say 1700, 1800 itself, people started thinking about it. And based on the Seebeck and again Volta effect, when we know that like if you have a certain solid materials like copper wire or something, if you heat it one edge, then it generated voltage, because electrons try to move from hot side to cold side. And based on this principle, there have been like last 100 years numerous amount of research article published where we can use waste heat to harvest some electricity. But the problem is like here again, if you increase the conductivity of the materials like high migration, then this material, the heat difference become very soon. This heat difference become neutralized, so we don't get any energy. So lots of different techniques are there, like lots of input in the material science, new materials, new theory has developed in these publications to get novel kind of systems where we can reduce the conductivity of the materials but increase the efficiency of the thermoelectric energy harvesting. But still, like after so many years of research, the most of these materials show a Seebeck coefficient of very small. That means it's around say maximum say 1000 microvolt of potential difference per Kelvin. So this is that still people are working in this area. So there is another things very last 10 years started, which is again based on the another effect called Tourette effect, which is again ionic system in the liquid state or solid things, where which says like if you apply a temperature gradient, it can also move the ions or other mass from hot zone to cold zone. So based on this effect, different polymeric materials where ions like hygroscopic materials which can have a liquids inside the polymers, we apply a temperature gradient, the ions move from hot zone to cold zone, then we can get some of the waste energy in the form of electricity. Similarly, another system is there where there are very few thermogalvanic redox pair where they shows different redox activity at different temperatures. So if we can apply a system where this redox activity can be taking place in hot zone and cold zone differently, then also we can get some of the energy. But the problem with this system is we have very few system, one or two system where we can apply this kind of effect, and this is very difficult to tune. So we can see like all within a 10-15 years, most of this Seebeck coefficient obtained with ionic thermoelectric materials in the range of millivolt range. Earlier, everything was in the microvolt range. It's a significant improvement, but there are problems like most of these polymeric materials are low ionic conductivity, lack of long-term stability, and these are all like not suitable for humidifying environment, and they are all are based on organic polymer based systems. So even they come in a like thermal shock. Anytime they come in contact with a high temperature, this get damaged. This is a problem for realistic application, because this material itself is targeted for harvesting energy from temperature difference, but they cannot tolerate exposure to high temperature. So this was the issue. So again, here we tried to explore our nanofluidic systems based prepared with vanadium pentoxide nanosheets, because vanadium pentoxide is an inorganic material. It's an oxide. It can sustain a very high temperature, and it also displayed a very high ionic conductivity, almost as good as Nafion. So this we believe to be a good system. So where we made a membrane and just connected a simple device with two copper wire connected to it through silver paste, and placed under a temperature gradient by making a Peltier device. Then you can see that ions can move from one side to another side. And these are the experimental data actually. This blue is the temperature gradient, which is around 7 Kelvin. Whenever we apply the temperature gradient, you can see a voltage development. And moment we stop the temperature gradient, go back to 0, then again this voltage goes down. Then we can do it as many times as we want. Moment we apply temperature gradient delta T, the voltage changing. Similarly, if we change the delta T from like minus 15 delta T is equal 15 degree to 15 Kelvin to 10 Kelvin, 8 Kelvin, 7, 4 Kelvin, the voltage also changes with increasing delta T. And based on this, we get a Seebeck coefficient of 14.6 millivolt per Kelvin. This is not the best, but this is the first example of ionic thermoelectric materials of layered material. This is still a very inspiring number. Similarly, we can also do lots of experiment to find out what is the actual mechanism of this thermal transport. Then by varying the humidity, varying the conductivity, and all these things, then we can see that the proton transport is the temperature gradient induced proton transport is the reason behind this observed thermolytic potential. So one of the key experiment to find out mechanism, like we can dehumidify this entire system, the device, putting it dehumidify and with so many desiccators. Then we can fill this chamber with D2O. Now H2O, we get a voltage of around, say, whatever voltage we get, say around 9.9 microampere current. Once we dehumidify and put it with D2O, the change decreases. This is because H2O is changed to D2O, and D2O is heavier than H2O, and because of this, we feel this difference is there. And similarly, we can, once we apply the voltage temperature difference, the ions supposed to move from hot zone to cold zones. Now, if you do a IV curve through this, we can see this IV curve is not going through the origin. However, we have a net non-zero current at zero voltage, as well as a non-zero voltage at zero current, which is another proof that ions are actually moving from one zone to another zone. This and we can also apply this voltage for a temperature difference for a long time. You can see voltage is almost unchanged for around 10,000 seconds. Similarly, current is decreasing with time, because unlike electronic materials, the ions are, once it's gone from one side to another side, it has to accumulate in some places. It gets charged. These ions cannot move to the electrodes. So it gets accumulated. As the ions are accumulating here, it will repel the incoming ions, as well as the ions are not generating here. No new ions are not generating here. So there will be not sufficient ion to move from this side. So the current decreases with time, but voltage remain constant with time. So another important properties of 2D material is that we can easily tune their nanochannels by functionalizing with different kind of materials. So we use to functionalize this V2O5 nanochannels with PSS polymer. Then we can again prepare a membrane and do the necessary characterization. Now we can see that Seebeck coefficient is increased to 26.3 from 14, which is an increasement. So like that, we can do various composition analysis, then different experiment we can do. Now to prove that the 2D nanofluidic channels is responsible for this good Seebeck coefficient, what we can do, that 2D sheets can be transformed into rods or bale kind of shapes. Now, if we take the bales, we don't get those channels. 2D channels where we expect to the ions to move through in a well-directed way. So these are the characterization showing that when you move these nanosheets to belts, there is no change in the chemical compositions or chemical structure. Only the morphology is changed from sheet to belt. Now, if we prepare a device with this unorganized vanadium pentoxide materials, then we can see we don't see any good effect. It was initially 14.6 for pure V2O5. With nanobelt, it is just 0.094. Similarly, with PSS, it was giving us 26.7, 17, but with the nanobelts, we got only 0.083. So this 2D layered structure is very important for this application. Same thing when we measure the voltage in the horizontal directions where ions can easily move from one side to another side, we get a very good voltage. But when we move from top to bottom through this zigzag way where it is very difficult for ion to move in this direction, we get a very small thermal voltage. Now, as we said, like this PSS membrane, like polymeric membrane, which is showing very good thermoelectric property, but if you heat it just 200 degrees centigrade for 5 minutes, it's completely destroyed. There is no question of measuring any thermoelectric properties with this membrane, but our membrane, if we heat it 200 degrees centigrade for 5 minutes, nothing happens. Its structure is intact as well as its performance is intact. So this is a very good advancement in that direction. Similarly, this material also has a very good self-healing characteristics. You can cut it into pieces, you can put them together in a small amount of liquids. Then again, you can see this structure is regained and its mechanical properties also regained. And with this regained structure, you can cut and damaged and heal structure also. So not showing any degradation in the thermal powers. So this is with this. So I would like to thank you. I don't have any conclusion slide here, but the point is like just simple using electrokinetic phenomena, we can have different ways of harvesting energy in the domestic environment, which may not be able to solve all the problem of the world,